If you measure a physical quantity, experiment may tell you many possible values of that quantity. For example, if you are measuring position, then experiment may tell you position is here, or position is here, or position is here. Another possibility is that you are measuring energy of hydrogen atom. That experiment may tell you ground state energy, which is minus 13.6 electron volt, or may tell you the first excited state energy, which is minus 3.9 electron volt. And these values you can calculate with Bohr model or quantum mechanics. Quantum mechanics calculation are later in the course. But anyway, if you have many possible values of a physical quantity, then quantum mechanics tells you not only the possible results of measurement, but also probability of each measured value. Then these things can combine in one numerical value. You know many values, many that are there, but expectation value is one value. And this lecture is to tell you that this one value is equal to an average of many values which I have told you, but equal in such a way, sorry, not equal, not average, in such a way that if a value has more probability, then that value is multiplied with a bigger number. So if a value has less probability, it's measured, it's multiplied with a lesser number. So that kind of average, which is actually more close to actual experiment, because in actual experiment, if you have a more probability, then that measurement will appear more number of times. So that realistic average is equal to expectation value. You remember what I've said? I've not said that the definition of expectation value is that average. Definition of expectation value is something else, and you should be waiting for that in the next slide. That definition is equal to that weightage average. That's the first lesson of this lecture planned. And the second is that purpose of this lecture is that I have to show you in 5 examples that whatever you calculate, either using definition or using this weightage average, whatever you calculate, the result of calculation would be what you expect, and the meaning should be clear as we do actual cases rather than discussion here. So I start the actual content of the lecture without further delay. As I said something is equal to weightage average. First, let me tell you what is weighted average means. Weighted average means that I spoke a moment ago, that if a value has more probability, then that value is multiplied with a larger number. So that's the weightage average. And expectation value is not defined to be weightage average. Expectation value is something else. This is what I'm showing you on the left hand side. That is expectation value. Why that is preferred in definition rather than right hand side, I tell you in a moment, but for the moment just to see it. When I've written it, I've written it in English as well. It is state, operator, state. And state appears sometimes once bra and once cat, so it becomes bracket, which is a number. And that's why is equal to a number, because on right hand side your probability is a number and eigenvalue is a value, that's a number. So I hope I have explained all the symbols. That's when I say physical, I just repeat. When I say of a physical quantity, then for physical quantity you have operator A, and in state, the crucial thing is that the state is the same left and right, and that is equal to value and is eigenvalue, and Pn is probability, and I hope I have explained our symbols. So the claim has reached you, and now the question is how to prove the claim. Namely, I have to how to start from left hand side and reach right hand side. That's the plan. And how to do that is the following: that because in your right hand side you have a sum, so think of that. What is the way to get a sum? And the answer is that you can have identity operator anywhere, like a number 1 can be multiplied, can be thought to be multiplied everywhere. But that trivial thing, identity operator, is equal to a sum, which is called completeness. And it's called completeness because it's a sum over complete set. Now the complete set is another name of the word basis. And where you find basis, that's a question, and the answer is a theorem in quantum mechanics which says that eigenvectors of any Hermitian operator form a basis. Now if your operator A, because I said physical quantity, so operator has to be Hermitian. So if it is a Hermitian, then eigenvectors of any Hermitian operator form a basis, and in this calculation the most convenient choice is that you choose eigenvector of this operator, this Hermitian operator, as basis. If you have done that choice, then the rest is trivial, because in that case, if that is eigenket or eigenvector, you can say, of this Hermitian operator, then eigen means that operator acting on eigenket, you can say operator acting on vector, will be replaced with this eigenvalue. And value you can take it outside bracket, and second bracket is unchanged, and the first bracket is because this is replaced with value I have taken it outside, and you have that bracket. And now for the next you try to see what is the relation between this and that, and the relation is, they are cat and bra are interchanged. That means one number, bracket is a number, now you remember, one number is complex conjugate of the second, and you multiply with a complex number with a complex conjugate, it's called modulus square. And a postulate of quantum mechanics says that this modulus square is equal to probability. Modulus square of transition amplitude is equal to probability. So if you replace this with probability, that's the right hand side, and that's all the purpose of this slide is. So the main theorems of this lecture to be used are complete, and what remains in the remaining portion of this lecture is that I have to apply this information. Now to calculate this information means ability to calculate expectation value, and you remember you have both things, both formulas at your disposal. And one of the things while doing each of 5 examples will be that you have to see your given information and then decide that with given information you can calculate left hand side, or with given information you can calculate right hand side. That will also be your test, and the result will tell you in each of 5 cases that the result either calculated left hand side or calculated by right hand side. Whatever you calculate, the result will equal to what we expect. The meaning of this word, this phrase, what we expect, should be clear with examples. So I better start examples. And Sorry, before examples, I have just summarized it, which I have already spoken, namely that out of this information which I am telling you, left hand side and right hand side, left hand side is preferred to be definition. And you may think why this is preferred. Because the name expectation value is more related to right hand side. Because in right hand side you have probability, and if something is more probable, if probability is more, you expect it more. So the name is from right hand side, and as I said in calculation, and out of 5 examples what I spoke about, in majority of examples I have to use this right hand side. But still, definition is this. So why this is preferred for definition and not that? And the answer is that in quantum mechanics a case starts with operator. Remember, if you have to summarize whole quantum mechanics in just one sentence, then you can say quantum mechanics is calculation of eigenvalues and eigenfunctions of operators. So the calculate what case it is, the answer is what operator it is. So your case starts with operator, so that's why definition is there. Although that is not binding on you that you always use that in your actual calculation to follow in this lecture, because if you have shown that from start to this we have covered all that is the journey. So if you have covered the journey, then that is also on your disposal. But you remember the overall thing in this lecture even started with this. So that is the definition. This was the later arrival. But now you have both. And with both, you start applying it. And you should be able to test to yourself whether given information allows you left hand side or right hand side. That thing I've already spoken. Now just see it if you can apply. So the first test of your ability, I hope, which is generated, is that if you are given that state, you remember the state is the eigenstate of a Hermitian operator, then expectation value is equal to eigenvalue. That the result is not written, result I have only spoken, but the question is written. If the state is eigenstate, the word non-degenerate means that for one eigenvalue you have one eigenstate. So you have one eigenstate and you have to calculate expectation value. So what is more convenient, I think, is the only possibility is which of the two information you can use for calculating this case. Remember, two information is, one information is the definition, which is psi a psi, and the other is the result, which is a and psi n. So which can be used here? And the answer is here, because your state is given, so you can use only original definition. Once you have done that, then rest is trivial, because here that is I already told you it's eigenstate, so operator will be replaced with eigenvalue and dot product will be psi n with itself. If it is normalized, that is 1 and that is eigenvalue. And now coming to the English issue, that why it is called expectation value, and the answer is that in this case, if it is the only possibility, then that is what you expect. And the calculation has also told you that. So the calculation is according to our expectation. So the calculation says, in this case, start with the psi a psi, and the result has been what we expect, because we could not expect anything else, because there was only one possibility. So that is one. So the next application is that if you have not one value, more than one value and each value has equal probability, like dice or coin or so, then what in dice you have a 6 and in coin you have 2. But expectation value should be 1. So how you can summarize 6 or 2 or any number of values into 1? And the normal expectation would be average. And because all probabilities are equal, so in average there is no reason to prefer any value over the other. So that is our expectation. Now let's see what calculation gives. Now I start calculation, and calculation says that if you have m equal probabilities, then each probability is equal to reciprocal of number of possibilities. Maybe I repeat. Each is 1 over number of possibilities. So that's a subclaim. So the subclaim can be proved by using the simple information that total probability is equal to 1. But rather than adding that proof, I think it's more interesting if you apply that formula for coin and then dice. In coin, you remember the number of possibilities is m. So in coin you have m is 2. You have to be careful about the indices what are used. M is 2, n is a variable. It can take value as 1 or 2. So whether it's 1 or whether it's 2, the probability is always 1 by 2, which is 50%. That's a coin. And in dice you remember, n runs from n is 1, n is 2, n is 3, n is 4, n is 5, n is 6. But the m is the total number of possibilities, that is 6. So every, whether it's P1 or P2 or P3, every probability is 1 over 6. Now I did not take your test. I have already shown you. You know, the test has been that whether you have to use left hand side, the original definition, or this result. But in this case, because your probabilities were given, so the only thing you can calculate is this weighted average of probabilities. So I did not take your test, but just shown the option because left hand side is not possible. So only option available is right hand side. So you put that formula in that. Tn is 1 over m because variable is n, so m is independent of n, so that goes outside the sum, and the inside you have a simple sum. So simple sum divided by number of possibilities, that is the ordinary average, and that's if you have to replace 2 or 6 or values by one number, then what other than average can be our expectation. So that is our expectation, and that is result of calculations as well. Calculation based on using the definition of expectation value. So the definition is giving you expected results. So that's the two cases. Now the third case is when your probabilities are not all equal. There some is large probability, some is less. So there will be test of the word weightage. In this case, there was weightage. The word weightage was actually a bit of irrelevant or not crucial thing, because you don't see any weightage. But if probabilities are not equal, then you see weightage. And now you think if probabilities are not equal, but probabilities are given, so which side of you have to use in your actual calculation? Original definition psi SI or this? If probabilities are given, and the answer is, I hope you have understood. If probabilities are given, then this you have to use. So the next slide as well, I use this, but this time probabilities are not same. So the probability of A1 is 70% and the probability of A2 is 30%. And actual experiment means you repeat, for example, 10,000 times. Sometime A1 appears, sometime A2 appears, and so on. This identical experiment set is called ensemble. So it's optional to use this term, but if you use, that's helpful. What you see is as an order it will be a random, sometime A1, sometime A2 and so on. So you see something like symbolically I can show you, you have many things. So sometime A1, sometime A2, but if because your number is large enough, so that means A1 maybe it appears maybe first time and then third and then fourth and then seventh or whatever it is. When you count total, then that will be approximately 77,000, and A2 total will be almost 3,000. Now when you take this time average of actual experiment, the name of actual experiment is ensemble, so that means average is ensemble average. So ensemble average would be what? A1 is appearing 7,000 times, so A1 is multiplied by 7,000, and A2 is appearing 3,000 times, so that is A2 is multiplied by 3,000. That is the total measurements and divided by the total number. And now you see it's approximate because we have not repeated infinite number of times, we have repeated only 10,000, so that's approximate. Now you see the next is no approximation, that is the actual calculation. So 7,000 divided by 10,000 is 70%, and 3,000 divided by 10,000 is 30%. And you recognize what these are. These are probabilities. So A1 P1 when n is equal to 1, and then A2 P2 when n is equal to 2. And that is expectation value. That is not the definition of expectation value, that is the result for expectation value. But whatever it is, we used it, whatever was available to us, but the result has been what you expect. Anyway, if the word expect is not clear, but at least that aim is achieved, that you have known how to calculate expectation value even in a case when probabilities are not equal. So at least that aim is achieved. So these are three discrete cases, and now I take up the case when number of possibilities are labeled by a continuous variable. And first I take up the case that the continuous variable is x position. Your measure and position can be anywhere, because it can be anywhere. So the possibilities are any real number between any interval, and the number of real numbers between any interval is infinite. So it's a continuously infinite possibilities case, and you are given wave function. So if you are given wave function, the main test remains there. Which of the two information you have to use? You remember, one is psi A psi, and the other is A and Pn. So what you use in this case? I hope the choice is obvious, because probabilities is not given, so you can use only psi A psi. Okay, psi A psi, but psi A psi is in bracket, but in bracket you have cat, but what you have is not, what you are given is not cat, but not wave vector but wave function. So how to convert wave vector to wave function? That's the question. And the answer is that this is a bracket, and bracket is a dot product, and dot product is a sum. Ordinary dot product is ax bx plus ay by plus az bz is a sum. That is if your possibilities are countable, then is a sum. Because here the possibilities are continuous x, so sum is continuous sum, namely integral. With this integral, you replace each component of vector. The component is labeled by x, that means it becomes wave function, and bra is complex conjugated. Now that's all for quantum mechanics, and now is a calculus issue, purely calculus. That value is given, you put in the value and you calculate. The first is the putting value. When you multiply this with complex conjugate e power iota, complex conjugate is e power minus iota, and they give e power 0, which is 1, so that doesn't, complex factor does not appear here, this becomes 1, and this real factor gets multiplied with itself, because complex conjugation result is same, so that becomes a double, and your x is already there. This integral is there. You can calculate it using a substitution as well, because if you take u to be x squared, then derivative is 2x, which is available. But a quicker way is, although that needs a bit of understanding, but it's quicker, is that we know your integrand, but we have to integrate, is an odd function. And integration is area under the curve. Because it's an odd function and it's symmetrical, as much is to the left as is to the right. So to the left is negative area, is the negative, and to the right is positive area. Although this is a different example, but anyway, if you have a negative area and positive area, then the total is negative and equal things cancel and the total is 0. So if you use the theorem, which is the name of the theorem is symmetrical integral of an odd function, and the theorem says its result is 0. So that will save your time. But anyway, whether you calculate by substitution or by this theorem, the result is 0. And now coming back to quantum mechanics, that in this case we were given wave function, and square gave you probability density, and probability density had peaked at x is equal to 0. So that is the value we expect most, 0. And the calculation has also given you 0. So what you expect is what you get by this definition. So that's the fourth example in which I have shown you. Now before turning to the fifth and last example, I give you an information that how you measure that. So far we have done calculus. That was the theory. And if quantum mechanics is science, that I should try as far as possible to relate that to actual experiment. And if that effort I do, then my effort is that if any position has more probability density, then that position will appear more number of times. Like in dice, you have all equal probabilities, so that all appearances are same number of times. But if you have weighted, just like side A1 has 70%, so that is more number. So where 0 has anyway, the middle one, which is in this graph, is not at 0, is at 3.5. Maybe you can't see 3.5, but I can see and I tell you. His peak is at 3.5, so 3.5 value is the most probable, that appears the most number of times. And the other value appear at respective number of times. And if you calculate expectation value, then this time, because your probabilities are given, this graph use chi-square give you probability density. So through that, and you have discretized it to probability density. From probability density, you calculate probabilities. And your probabilities are given, so you can calculate only the result, not original definition. The result is, this is A and Pn, but rather than An I have Xi, because each value is Xi, and the probability of each value is Pi. So A and Pn becomes Xi Pi. Now next is an approximation that Pi is proportional to number. Approximately proportional. The reason for approximation is that I have not repeated the experiment an infinite number of times. If you repeated it for a finite number of times, then probability will be proportional to number. If all probabilities are same in dice, all numbers are also approximately same. If probabilities are large, I showed you 70%, 3%. So 70% as 70% number of times. If it is 30%, it's a 30% number of times. So that's a proportional. You have 1 divided by total number of possibilities as well, because 7,000 was divided by 10,000 and 3,000 was divided by 10,000. So that's so I hope you have understood that approximate equality. And the next approximate equality is that we have to calculate is sum, but because in actual calculation, if wave function is given, then we can replace I, discrete I with continuous x, xi becomes x and summation becomes integral. So this summation is approximately equal to integral, again because of finite number of terms you have taken. And the calculus result is what I showed you in the previous slide, was 0 or in general equal to peak value. So that is what the result of previous has to do with the actual experiment. The result is nothing new. Expectation value is equal to peak value, and peak value is most probable value, and that is what you expect. So I've repeated in a fourth case that expectation value is what you expect. And the next is the last case, and then I finish this lecture. And the last case is to tell you that that you can calculate expectation value for any physical quantity, not only position. So the second physical quantity I've chosen is momentum. And remember, the remaining physical quantities can be constructed out of position and momentum. So once you learn position and momentum, in the remaining lectures I can tell you how to calculate expectation value of other physical quantities. So for preparation, in addition to position, momentum is sufficient. Now how to do that? In that case, the same thing, but as in position, but the only difference is that momentum operator with position wave function is not x but minus iota h bar d by dx. So that's all quantum mechanics is of this case. The rest is calculus. And in calculus, previously you had only integration because it was x here. Now you have two things in calculus: first differentiation and then integration. And differentiation of that exponential remains unchanged, and you take derivative of power. X square derivative is what you recall your calculus. I give you 1 minute, and what is derivative of power? And now I show you the result. X square is 2x, and that's 1 over a square is unchanged, and plus that x derivative is 1 iota k naught. So that's the differentiation. And now comes the integration case, and the first term is x e power minus x. That integral is same as the previous case. It is a symmetrical integral of an odd function, that is 0. So the second is iota k naught goes outside, and you have to integrate only that you recognize what it is. That's a Gaussian function, and I have a separate video which is 6a for Gaussian integral. That's a Gaussian integral formula is that you should memorize it like you have memorized hopefully some way or other power rule or trigonometric or integration by parts, if so, and so on. So to that list you should add Gaussian formula, and the formula you have to memorize. What else I can do? Help. And the formula is that. We don't need spending time on what is the result. The crucial thing is that we have learned how to calculate expectation value even for momentum. The rest are, it's up to you how much time you spent on that, whatever value, or h bar k is momentum, or so that's all momentum. That's you can take your time in seeing it, but the main purpose was to teach you how to calculate expectation value in a variety of cases, and the second variety has been momentum. So that's all this lecture, and now I summarize and in form of conclusion, and then I finish. And in the conclusion is that throughout lecture we have been deciding between left hand side and right hand side, and left hand side was psi a psi, that is the operator, and right hand side was an pn, which was a weighted average. Now the definition prefers operator an psi. The reason of that preference is Then quantum mechanics, if you want to summarize quantum mechanics in one sentence, that is that quantum mechanics is calculating eigenvalues and eigenvectors of operators. So our case, every calculation starts with operators, and that is our definition. That's the definition. But the result we achieved in this lecture is that a weighted average. That means this definition is equal to weighted average. Once proven that this was also result, weighted average was also at our disposal, and we have according to need, and I think 2 out of 5 cases I have preferred. It's not that I preferred, that was the only possibility using given information to use this weighted average, 2 out of 3, and in 3 cases I used original definition, and every time the result has been what you expect. So explaining why it is called expectation value. So that's all in this lecture. Thank you for watching, and do not forget to subscribe to this channel.